All right, man. We're gonna do some experiments tonight. See if I got all my stuff ready. I do. I think I got it all set. Time to do some experiments. Let's see what we're gonna do. Let's add a little base over here on the left. Oh, I should probably get my gloves on. Oh, that's pretty little colors going on. Yeah, got a little violet in the middle of the vortex. We had some orange red at the top and some yellow at the bottom. Let's add another drop of base and see what happens. Let me get these gloves on here. All right. Give her another drop of sodium hydroxide base. Here we go. And it goes. All right, let's try another. You know what? I think I need a little bit more universal indicator dye over there on the left. I just want to get the colors to pop just a bit more. Let's give another squirt here. You can also see, right, when I add the universal indicator, how the material stays concentrated in the center of the vortex. I'm used to seeing that, and it makes sense if you think about it, because, you know, just like the eye of a hurricane is low pressure, the eye of that vortex is low pressure too, and so material is going to tend to stay in a low pressure region. I don't like that. I like that view a little better. All right, let's add another drop of base. Let's do it over here on the right. Here we go. Drop of base on the right. Over here, we got a slightly smaller vortex. Actually, quite a bit smaller. Come on, baby. Look at that. We got a little rainbow action going there. Oh, it looks like a little traffic light, kind of. It's pretty. Thank you there, Xmas Moxie. Let's add a little more drops to each. Here we go. A little drop over here on the left, a little drop on the right. I'm adding sodium hydroxide. Boy, those flow patterns in the smaller vortex are just beautiful. How you doing there, Jimmy? Thank you there, Yo Migs. Appreciate it. Add a few more drops over here on the left. Let's get the stir speeds even. So the stir speeds now are the same, the revolutions per minute of the stir bars. This is a larger stir bar, so you can see a larger vortex. Over here on the right, that's a smaller stir bar. All right, adding some acid to both sides. There we go. Pretty, huh? I love those colors. Oh, that looks nice, huh? That looks kind of cool. Trying to get the lighting just right. Sometimes I get the lighting right, it just really looks nice. I don't know, did I like that better, like this? I don't know. It's kind of hard to tell because my safety glasses are also sunglasses. A little tough to tell. I think that looks nice. Now add phosphorus. I got no phosphorus. At least not elemental phosphorus. I'm going to go ahead and add a drop of acid on the left, a drop of acid on the right. The acid I'm adding is hydrochloric acid. It's the same acid that's found in your stomach, except the stuff that I add to this is like 100 times more concentrated than what's found in your stomach. All right, let's add some base over here on the... Come on, man, broken. Let's add a base over here on the right. I'm going to zoom in just a bit so you can see the flow patterns. All right, here we go. Let's add a little drop here, drop of base. See if we see something pretty. Look at that. Come on, man. It's just gorgeous. It's like a whole traffic light. Red, yellow, and green. Thank you there, Caleb. Thank you there, Bilotti. Forgive me if I don't say your all names correctly. Look at that. Come on, man. That's just gorgeous. Oh, I think that's so beautiful. And if we do the same thing over here on this side, it's not, you know, the vortex is so large. Just things look a lot different. But you can see like the material stays in a wider vortex column. Vortexes, huh? Drop a base over here. Me too, Sunday. Let's do a drop of base over here. See some beautiful pattern. You can see that pH started at like 7. Green is neutral, pH 7. And then when I add the base, of course, it jumps up to violet, which is going to be a pH 10. All right, let's see. Let's see if there's... Oh, man, that's pretty. I think that's going to be enough base. We're going to make this basic pretty well. So you can see here the pH scale. So these are the different pH values you'll see, the colors you'll see. Hold on, let me turn on the light so you can see these colors a bit better. So these are the different colors you'll see at different pH values. So right now we're about a pH 8, yeah, which is somewhat basic. Add a super base, huh? This is the strongest base I have, is 20% by weight sodium hydroxide. Let's add another drop of base over here on the left. And now we're going to go back to adding acid, and we'll look at both of them at the same time. All right, here we go. All right, drop of acid on the left. Let's do 2 drops. 1, 2. 2 drops of acid on the right. 1, 2. It looks like it, doesn't it, Sunday? Look at that, man. That is a really nice color we got going over here on the right. You know, the larger vortex, it mixes the material quicker, so that the colors don't persist quite as long. Papa Smurf wants some peroxide. I don't have any peroxide, Papa Smurf. Oh, wait, I do. I got some peroxide. All right, here we go. I do got some peroxide. So what I'll do, Papa Smurf, let's just do this. So I'm going to go ahead and add, we'll put this here in the middle, all right? And to this one, I'm going to add, there we go. I'm going to add a bit of base to this to make this basic, because in my experience, peroxide tends to work better in basic conditions. So I'm going to go ahead and make this basic, and peroxide tends to oxidize dyes and make them colorless. That's what I'm hoping is going to happen here. So I went ahead and made this particular flask. I made this particular flask basic. How do I know it's basic? Because here's my pH scale, yeah? So, you know, I made this pH 10. And I'm going to add some peroxide to this. Hydrogen peroxide. This just, you know, this stuff you can buy at Walgreens. I'm not selling anything, though. It's just where I got it. And then what I'm going to do, happy holidays there, Beardwing. And we're going to go ahead and add some peroxide to this flask and just see what happens. So in it goes. I have no idea what's going to happen. But in goes the peroxide. My guess is nothing. But who knows? Who knows? I don't know if that's going to fade or not, but we can leave it there and you can all let me know what you think, okay? Ulysses, I do have some videos on D2O. You can check out my YouTube shorts. I've got quite a few videos on the chemistry of D2O. Man, that was a beautiful flow pattern there on the right, wasn't it? But I do not have any D2O with me right now. Can I turn water into wine? Unfortunately, I do not have the materials with me to do that particular experiment. I apologize. Oh, you thought I was going to pour this into the vortex? I mean, I could, but I don't want a bunch of peroxide running around in here. I don't think it's doing anything here. Is it? Is it fading? I don't think it is. I'll turn it acidic in a bit, and we'll see. Hello there, Sandra. All right, let's, or Sandra, however you say it. Sam Reyna, I already have some videos where I do that. Check out my YouTube shorts. I've got quite a few videos where I put sodium in water, lithium in water, potassium in water, and even calcium in water. If you go through my YouTube shorts, you'll find quite a few of those. Me too, King Jax. Hello there, Oof. So someone's asked, that's Error Games has asked, Ulysses, that'd be kind of cool. Chicken leg and peroxide. Hello there, fun. Hello, Jenna. Nice, Sam Reyna. Okay, somebody asked what is going on here. So what I am doing in this experiment, or I should say these experiments, in each flask, I have some universal indicator. Universal indicator is also known as rainbow indicator, and rainbow indicator changes color depending upon whether it's in an acid or a base. And it's really specific. It'll actually change color with pH. So here's our, hello there, stars. Here's our pH scale that universal indicator displays. So over here in this flask, I see it's like an orange color. That's going to be pH 5, which is slightly acidic. Over here in this flask, it's kind of green, greenish yellow. So it's somewhere in between neutral and just slightly acidic. That's all I'm doing. And then I add, I'll add some stomach acid. This is the, over here, this stuff, it's the same stuff. I'm going to add it over here on the right, same stuff that's in your stomach, hydrochloric acid. It's just that drops of this stuff are like 100 times more concentrated than what you find in your stomach. And you can see as I added the hydrochloric acid, this shifted from that sort of neutral color to, well, you can tell it's like getting more, you know, orange or red. Actually, it's shifted to a yellow color once everything homogenized. Over here on the right, I'm going to add a base, sodium hydroxide base. It's also known as lyes. I'm going to add 2 drops over here. And looks like we went from an orange color to... Hey, all right, RL. Go blue, baby. Looks like we went from an orange color to a green color. So you can see when I added base, the base neutralized the acid. And if I continue to add base, which is what I'm going to do, I'm going to add 2 drops over here. 1, 2 more drops. We're going to go from neutral. Orthodiethanyl what, Bilotti? Looks like we went from like a pH 7 or so to pH 10. Ulysses, toothpaste tends to be slightly basic. You know, like pH 9, I'd say. I'm going to add some drops of base over here on the right. Oh, that's beautiful. Such pretty colors. A couple differences you may see. That's correct, King. The base neutralizes the acidity. So I'm going to go ahead and now watch this, King. Over here, I'm going to add acid to this. So I'm going to add some drops of acid. Here we go over here on the left. 1, 2. And look at that. We see that the acid neutralizes the base. So they neutralize each other. Benzyl anion. Put xenon in there. I don't have any xenon with me here. Another drop of acid over here on the left. 1, 2, 3 drops of acid on the right. Hello, Ahmed from Egypt. Very nice. I apologize that I can't read. I think that's Arabic. What are these called? These are 2 flasks that contain universal pH indicator. That's going to depend there, Shirelli. That's going to depend on your diet. So I have universal indicator on both, actually all 3 of these flasks. And I'm adding acid to both of them. Actually, let's add a drop of acid down here on this guy too. Then it goes 2 drops. Give this a swirl. Give that a swirl, see what happens. And you can see the respective color changes that occur as you add either acid or base. Mohammed, I'm using 20% by weight hydrochloric acid and 20% by weight sodium hydroxide. Thank you there, Gigabean. And it's, in the middle one, it's the same stuff. It's just not being stirred. I also added, somebody wanted to see me add some peroxide to one of these. So there's some hydrogen peroxide in this middle one as well. And I just added some drops of acid to this middle one. And you can see that the color has shifted to green. I'm going to go ahead and add some, let's add some base over here on the left. Excuse me, the right. We're going to add some base over here on the left. Kevin, you got it? Kevin wants to see it as acidic as possible. Luke, the spinny things are made of steel. They're just little iron steel magnets. And, you know, they're resting on a magnetic stir plate. Inside the stir plate, there are what I would like to call magnetic fan blades, and as the fan blades spin, it causes the little stir bar to spin. Somebody asked to get this as acidic as possible. There you have it. That's as far as my pH meter or my pH indicator will go. At pH 3 and lower, it will remain red. So once we get to red, it's sort of at the end of its limit. What would happen if something was put into a high acidity solution? Would it dissolve? King Jacks, that depends. It depends on the acid, and it also depends on the thing that you put in there. But indeed, if something's strongly acidic enough, it will dissolve most things. I don't have any of that there, SS Sky. How does the indicator change colors? Asked Red Beanie Shay. Okay, Red Beanie, that's a complicated question. We're going to just talk about one of the dyes. Hey, look at that. For those that celebrate, looks like we got some Christmas colors here, don't we? You got it, Luke. So here's the way this works. I'm going to go ahead and add a drop of base over here on the left. Excuse me, the right and the left. So we get a little color shift going on. So in both of these flasks, there's a mixture of dyes. Those dyes are thymol blue, methyl red, bromothymol blue, and phenolphthalein. So these are, here they are. These are the different colors that thymol blue shows at different pH values. Here's the color that methyl red shows at different pH values. Here's the colors that bromothymol blue shows at different colors. And here's the colors that phenolphthalein shows, at different pH values. When you add up, all of them in a particular pH range, it gives the resultant color. Now, just to give you an idea on how one of these works, one of the molecules that is present is called phenolphthalein. And I talk about phenolphthalein because it's the simplest of them. Phenolphthalein only displays two colors in this particular system. The two colors that it displays are either colorless, like water, or pink, like strawberry Kool-Aid. And it works like this. When there's a lot of acid around, there's a lot of chemical species that we chemists call protons. We're going to signify protons. Look at those beautiful colors. Thank you there, Oof. I don't have any osmium gigabean. So we're going to signify proteins by this white cap. The phenolphthalein molecule is like this. It's like a ring shape if it's bound to a proton. If the proton is removed, the ring shape pops open. When there's a lot of acid around, there's going to be a lot of protons around. So the phenolphthalein is going to easily grab onto one of those protons and become ring-shaped. Thank you there, King. I appreciate the subscription. Yeah, I went to school for a long time, Red Beanie. So when it's shaped like this, the phenolphthalein molecule is colorless. Now, when there's a lot of base around, there's not much acid. And what bases do is they take those protons away. They're proton acceptors. So a base will take this, and when that happens, the phenolphthalein molecule goes doink like that. It opens up, it goes boop. And with that change in structure comes a change in color from colorless to pink. And that's what's going on with just one of the molecules in this system. Let's add a little bit of acid over here. Add a little acid over here. We're going to add one more drop of acid right here in the middle. I wish I had a little stir. I do. Let's just stir this down here like this. We got that kind of like a yellow-green color. Is gallium dangerous for humans? Dinoversum, no. You can hold gallium in your hands. I've done it many times. Yep, not something you need to worry about. All right, I'm adding drops of base now to all three. A diamond is indeed carbon. Papa Smurf, I've got a video coming out tomorrow on diamond where I actually burn it. You can actually burn diamond. So be looking for that tomorrow morning. Be looking for a video on that. How much acid do you need to vaporize a chicken that's 6 feet tall? Kevin, I think about 1 liter of 12 molar hydrochloric acid would do it. I think that would do the trick. That's very concentrated, by the way. I'm adding acid right now to both flasks. Thank you there, Oh boy, the comments are coming through a little quick there. Thank you there. Hey, King, let me know how you like the Burning Diamonds video. If you got cuts on your hand, you shouldn't touch gallium. Probably not. Hello from India there, Shirelli. How many times can you change the color before the reaction sees any difference in the speed? I don't see a whole lot of difference in the speed, to be honest with you. Hardy, I don't mess with uranium. I do not mess with radioactive material. Nope, not going to do it. It's not good for you if you don't know what you're doing. And I don't know what I'm doing. I know more than most. I know enough not to mess with it. Hey, Fenny, welcome back. Yep, you got it. Gigabean, I've done that. Gigabean, what I do in this particular video, in my, I've done it before. I actually published this video first. I did it way back in, I think it was around 2016 when I did this. What I do is I liquefy oxygen. So I get a test tube full of liquid oxygen. And then I get a diamond heated, in a blowtorch. And then I drop the diamond in the liquid oxygen and watch what happens. It's gorgeous. Can I name the whole periodic table, says Hardy. You want to see me naming the whole periodic table? Well, how do you know that I'm not reading it off? This is sick. Also, with editing lattice structures, would it be possible via FM and other kinds of magnetism? I don't know what you mean by FM. Could this indicate a specific reaction, such as a pH change, or is it related to the interaction of the acid with an indicator or another compound? So this is indicating just about everything you mentioned there. It is kind of, in this sense, indicating the reaction between hydrochloric acid and sodium hydroxide. But it's also a variety of indicator dyes in here that are changing structure. And as they change structure, and with a lot of protons around, or the absence of protons around, the molecule either grabs onto protons and undergoes a structure change, or loses protons and undergoes a structure change. And with those structure changes goes, changes in color. Yeah, I'm here, Natalie. How much does it cost you to do this stuff? Not much, Kim. The indicator cost me about $10 a half liter. The stir bars cost me about $40 a piece. It does look like a dust devil. You too, Fenny. Happy holidays. Merry Christmas. Yes, I'm using a real diamond, a dinoversum. It was about a point. I already did the experiment. The diamond's gone. I burnt the sucker. I mean, it is completely gone. Thank you there, Chelsea. How diluted are the indicators? Red Beanie, I put about 4 squirts into these flasks, which are about 1 liter each. Which has a more energetic reaction, an acid or base, and you show us. So LL, the black, the reaction is between the acid and the base. And it actually turns out that in this particular reaction, there's a unit in chemistry called the mole, and this reaction releases about 57. Well, let's go to calories, because you're probably more familiar with calories. It releases about about 200 calories. It's actually kilocalories. 200 kilocalories for every mole of the reaction that happens. Mighty Mouse, I do have a slow motion camera, and that would be an interesting idea to record this reaction in slow-mo, especially the small vortex. Hey, cool, Fenny. All right, so Gigabean, a hydrofluoric acid can dissolve glass. Brandon, what I am doing here is I am adding either acid or base. Right now I'm adding base to a flask, or to both of these flasks that contain, and even this one here, that contain universal indicator. And what universal indicator does is it indicates the pH through color. pH is just an indication of how acidic or basic something is. So as you see green, when you see green like this one over here, well, actually this one's kind of green. This is neutral. It's neither acidic nor basic. This one over here is slightly acidic. And I'm going to go ahead and add a bunch of acid to this flask over here on the right, And as I add acid to the flask on the right, you're going to see a shift to an orange, yellow, or red color. The redder it gets, the more acidic it is. Over here on the left, I'm going to go ahead and add a bunch of base. And you see as you add base to the flasks, it becomes more blue or violet. I don't know, Flying. I have no idea. It doesn't look like our peroxide experiment is... It doesn't look like the dye is getting... doesn't look like the dye is getting oxidized, so... I don't think the peroxide did a whole lot. Thank you there, Fenny. You got it. You got it. Hardy, I'm not going to do that. Brandon, I'm not going to do that. I've already done the peroxide down here in this one. You can see it. It has no effect. The densest element, gigabean, if I remember correctly, is osmium. What material is most valuable? Ulysses, what a great question. I don't know. Chillflex Design. I can't get it to pink. I apologize. The only colors you're going to see are these right here. Those are the only ones we're going to get. Thank you there, Dizzy. I appreciate that very much. Yep, Zaza, over here in the United States, we use the word alkaline and basic synonymously. It's just, we Americans do that. I apologize. You guys got to get used to it. I'm so used to doing it. It's just the way we roll over here in the United States. We call it acid-base chemistry. But I don't have any butane. Thank you there, Mighty Mouse. Let me know what you think of the diamond reaction. Sorry there, Butta. I'm not meaning to ignore you. I just don't have any butane. What's your favorite element? How about we all drop our favorite element in the chat? Mine happens to be hydrogen. What is the exact name of the color in small glass? I want to give nail paint... Yeah, I don't know what to call that. It looks red to me. Can I turn it blue? You got it, Natalie Cookie. Here we go. Let's go for... It's Buddha. Sorry, Buddha. Sorry, Buddha. Oh, shoot. Oh, I'm so sorry. I murdered names. I apologize. We're going to try to make this blue here. Mighty Mouse liking some hydrogen. Flying guy likes some argon. Oof likes the dioxide. Smeety likes potassium. Gigabean likes some oxygen. What do you think? Is that blue enough for you? It's got a slight green to it, but I'm hoping that that's blue enough for you. Gigabean. All right, Natalie. Natalie, let that slide as blue. I appreciate that. I agree there, Set 42. Set 42, what's going on, buddy? I like carbon too, Dizzy. Why, Fenny? Thank you there, Mammon. Lewis likes some fluorine. Papa Smurf, here we go. Hydrochloric acid over here on the right. We're doing some science experiments, Set 42. Elijah? Can cesium burn? It sure can. What's this here? What is the most difficult math equations you often use, or do you not do mathematics except in balancing equations? Zaza, I'm a physical chemist, and I would say probably the most difficult mathematics that I use is probably going to be, I'm going to say differential equations. Although those, they're not too tough. When I start having to get into using a bunch of matrices, I start getting a little bit lost. I have to get some help. Natalie, I've done a shorts video on elephant toothpaste. You're going to want to check it out. If you go to my shorts and go to popular, I have one on elephant's toothpaste that has roughly 1 million views. So you should be able to find that one fairly easy. So it'd be about the 30th one down or so. What is the base to acid ratio of the container now versus... Red Beanie. So let's talk about that. Red Beanie wants to know... You got it, Dizzy. I'm going to turn it purple. Red Beanie wants to know what's the ratio of acid to base, which is a great question. Now, it's going to depend on the color. So what I'm going to do first is I'm going to make it green, okay? Red Beanie, I'm going to make it green. We're going to answer Red Beanie's question here. How do you apply differentials in chemistry? There's, like anytime there's time-based phenomena, you're going to use differential equations, right? D by dt. So, when you're studying how fast chemical reactions go, you're often going to use differential equations. Often, also when we study sort of the electronic orbitals, we got to use the Schrodinger equation, which, of course, there's differential equations involved there. Okay, so can I do a reverse rainbow? Fenny, I'm not sure what you mean. So here we go. Over here on the right, I'm going to answer the question about ratios now. So over here on the right, this is green, which is neutral. So in a neutral flask, the ratio of acid to base is 1 to 1. That's because they're equal, right? That's what we mean by neutral. When we say neutral, we mean that that there's an equal concentration of acid and base. Now, if that pH changes to pH 6, which is what I'm going to try to do over here on the right, if I change this to pH 6, here we go. I'm trying to make it acidic here. I'm adding, Randall, I'm adding either acid or base to universal indicator to try to change the pH. Trying to get it to yellow. I think we can go ahead and call this over here on the left yellow. Okay, so over here now, this is yellow, which is a pH 6. So at pH 6, what you'll see is we're 1 unit below neutral. But on the pH scale, 1 unit is an entire power of 10. So here, when we go from pH 7 to pH 6, there is actually, you've increased, every time you go this way, you increase the concentration of protons, the concentration of acid by 10, but you also decrease the concentration of base by 10. So when you see yellow, because it's 10 times 10, 10 times more acid, but 10 times less base, the ratio of acid to base is 100 to 1. And then here, what's 100 squared? It's 10,000 to 1. And then it's 1,000,000 to 1. Yeah. Let's see, 1, 2, 3, 1, 2, 3. Yeah, here it's 1,000,000 to 1 at this place. And then we got to go 100 million to 1 acid to base. And in the opposite direction, if we go up to pH 8, the concentration of base to acid is 10 to 1. If we go to pH 9, it's going to be 100. Yep, it's going to be 10,000 to 1. And here it's going to be 1,000,000 to 1. So that's how that works. Yep, they go by powers of 10. If I turn it upside down, it's a reverse rainbow. Got it. So you want to go purple to red. Got it. Got it. Sorry for the little excursion into some mathematics there. Any element you like the smell over the others? What an interesting question. Well, I like the smell of, I don't know if this is really the smell of it, but, come on, man. I mean, food tastes so good. And a lot of food, is going to just be organic compounds, which is going to contain a lot of carbon. So I got to say, I must like the smell of carbon. Sorry there, Randall. I know sometimes it gets, unless I'm like, with a chalkboard and writing things down, it can get rough. Sodium hydroxide is going to taste very bitter, Ulysses. Any benzene groups, Anthony? I don't know, man. Smeedle, the acid I'm using is 20% by weight hydrochloric acid. The base that I'm using is 20% by weight sodium hydroxide. Rantos, this works indefinitely as far as I can tell. Is cabbage juice used as an indicator in professional chemistry? Not really, flying guy. Okay, here we go. We're going to try the reverse rainbow here. I've got everything nice and basic. I'm going to try to add some acid over here on the left. 1, 2, 3, 4, 5 drops. We're going to try the same over here on the right. And we got a little reverse rainbow going. Look at that. Come on, man. Hello there, Theokyla. What's the scariest element? Wow. I would say fluorine, Mark. You got it, Rantos. Thank you there, Fenny. I'm not sure we did a reverse rainbow real well, but it's hard to do the reverse rainbow. Papa Smurf, sodium hydroxide is not quite household bleach. Household bleach is sodium hypochlorite. So sodium hydroxide is a sodium, an oxygen, and a hydrogen, NaOH. Sodium hypochlorite, which is in bleach, is a sodium, an oxygen, and a chlorine atom. So it's sodium hypochlorite, NaOCl. Oh, that's base. Dinoversum, I have never used cesium in water. I've only gone with rubidium in water. That's as far down the chart as I've gone with putting metals in water. The indicator push is a universal indicator. The red liquid in the middle is the same stuff that I have on the sides. I just haven't been adding anything to the middle. Here, let's add a drop to it, okay? The red liquid in the middle is just my universal indicator. I just added, I think I added a little bit of base to it. If I give it a swirl, oh, there's still quite a bit of acid in there. Let's give it another swirl. Let's add some more base there. Can I explain the color change? Sure, we can. We can explain that color change. So I'm not going to be able to explain it in great detail. You let me know if you want to go any deeper than this. But in universal indicator, there is a mixture of 4 different dyes. Those 4 different dyes happen to be, let's see, it's bromothymol blue, methyl red, thymol blue, and phenolphthalein. Only NJ, I saw a chemistry professor do a bunch of experiments in class, and I thought, man, that's what I want to do. So here's the colors that thymol blue displays with pH. Here's the colors methyl red displays with pH. Here's the color bromothymol blue displays with pH. And here's the colors that phenolphthalein displays with pH. Of course, if you add them all up, like, you know, adding them all up across this pH 5 region, you get a yellow and orange, a yellow and colorless. That's going to tend to look like a little bit orangish yellow. So that's why we see that at pH 5. That's kind of how it works. It is a fruit punch color. So Cookie, what's happening here is I'm adding either acid or base to some flasks that contain universal indicator. No, I haven't, Dino. Here we go. Do I use any electrons to spin the steel? There we go. Let's try here. I'm going to add some base to both these. Let's see if we can get the rainbow going. A little bit over there on the left. Come on, baby. Give me a rainbow. I love it. Got a little flash of the rainbow over there on the left. Thank you there, Fenny. Oh, we got a nice rainbow action there on the right as well. Excuse me. I can't make one of them tan, Fenny. That's not one of the colors that this mixture of indicators will display. We got the rainbow, baby. James, whatever language you wish. I dare you to combine the red glass to the other glass. Here, let's do that. That's kind of fun. All right, let's make this. This one's basic over here. Let's make this one nice and red. This is fun to do. If you've been paying attention, you know what's going to happen here. I'm gonna mix red color with red with violet here in the middle, and we're going to see what we're going to get, okay? Let me make sure that's red. Okay, we got red on the right, we got blue on the left, or violet on the left. We're going to mix them. There we go. You can see up here at the top, I'm going to take out a squirt of violet, take out a squirt of acid. Whoop, that's basic. That'll fix after a while, I think. We'll get there. We'll get there. Looks like we're getting there. Mix them babies up. Well, looks like the the acid that I'm using is less concentrated, so just give me a chance here. Try putting a base and an acid in one at the same time. Yeah, we can do that, Fenny. Boy, it looks like that's a lot more basic over there on the right, on the left. Yeah. So even though I mixed equal amounts, it stayed violet. Because my base is quite concentrated. Let me fix that. Let me add a drop of acid over here. There we go. Another drop. All right, now we're going to try this again. Actually, I made it too acidic. Let's try her again. Put a drop of... There we go. All right, let's try her now. Thank you there, James. I appreciate that. Why is CO2 and H2O not flammable when they both contain oxygen? Well, here's why, Gigabean. Here's why. When things burn, they produce carbon dioxide and water. Yeah? Now what happens? So when you burn a carbon-containing material, what happens is you burn that in oxygen gas. So what you basically need is a carbon-containing material and oxygen gas, or O2. And then what happens when that carbon-containing material burns, it gets converted into carbon dioxide and water. And so carbon dioxide and water represent, so to speak, burnt forms of carbon and burnt forms of oxygen. They're already burnt, so to speak. So carbon dioxide is already burnt, and water is already burnt, in a manner of speaking. So you can see here when I mixed the violet and the red, I got a green color. They neutralize each other, as expected. How you doing there, Conboy? What's it smell like? It smells just a little bit like alcohol because they dissolve the indicators in alcohol. You got a Gigabean. All right, let's add some acid over here on the left. And over here on the right, we're going to add some base. See if we get a little rainbow going on. Hey, Fatima, what's going on? Add 4-nitrophenol. Push proj, that would be colorless to yellow, yeah? I don't have any of that in any of these flasks. Can I mix red and green? You got it, JH. Let's do that. Come on, man. Let's do some red and green. Some people want to be celebrating some Christmas out there. This is for those of you that celebrate Christmas. I realize not all of us do. There are some of us that don't. And I'm happy to do whatever celebrations you all want to do as well. But we're going to do some red and green here. It is getting near Christmas time. A lot of folks here in America celebrate Christmas. A lot of people all over the world do. Hey, there you go. We got some Christmas colors, eh? What do you think? Got some red, got some green. Yeah? Is a base or acid more dangerous? Audio cache, whether something is acidic or basic doesn't necessarily mean it's dangerous. So, for example, ascorbic acid is vitamin C. Citric acid you drink every time you drink some lemonade or orange juice. So really, it's not necessarily acidity or basicity that's dangerous. What type of color of green is on the left side? I don't know, NJ. Looking green to me. So this looks orange to you? That looks red to me. Yeah, I see what you're saying. What kinds of acids are there? Asked Fatima. There's a whole bunch of kinds of acid. There's acetic acid. That's basically vinegar, like 5% acetic acid. Have you ever done a witch costume at Halloween and made it seem like you're making something poisonous? Yeah, sorry, you said potions. Yeah, I absolutely have done that. Okay, here we go. What chemical causes spice? Wow, there's lots of different, like vanillin. Vanillin, you can probably guess what vanillin smells like. There's a compound called vanillin that is responsible for the odor of vanilla. Turmeric is yellow because of a compound called curcumin. So here I mixed the green and the red, and they ended up yellow, and that should make sense. So what you're going to see anytime you mix two colors, right? So we mixed the red and the green. They're going to neutralize each other, so they're going to go toward each other. So the pH 3 got less acidic, and the pH 7 got less basic, and they met together here at the pH 6. Capsaicin, I'm loving me some capsaicin, Gigabean. Yeah, capsaicin, that's responsible for the spiciness of hot peppers. I love capsaicin. How do the magnets spin? Oof, they spin because down here, obviously, there's a magnet, and they're sitting on a magnetic stir plate. So inside this box down here are fan blades that spin, and the fan blades are magnetic. Chartreuse and vermilion. Fenny, you're going to have to... Are those colors or spices? Why is cesium named after sky blue? Because when cesium is burned in a flame, it gives off a blue color. The NMR peaks of this reaction. I have no idea, buddy. You're going to have to look that up and let me know. No clue. No clue what the nuclear magnetic resonance of this is going to look like. Except maybe just washed out by a bunch of water protons. Can you make green, red, and blue? 18 p.m. in America. It's about right. More like 19 p.m. 1 a.m. in Europe. Can I do a collab with Nile Red? I'd love to do a collab with Nile Red. He doesn't even know who I am. He has no clue who I am. So it's probably not going to happen. Can I make this solution pink? I cannot. How fast does the spinning thing go? Let's find out here, all right? Let's turn this baby up. We're about halfway on this side. Here, let me turn this side up first so you can see what happens. I'm going to turn this max speed. We're getting close. See, that's what happens usually to the large stir bar when it goes too fast. It gets knocked out of orbit. You guys want to do a precipitation reaction? A double rainbow. I can try, Fatima. Oh, I see. So we got like a chartreuse over here. Probably not, Jordan. Papa Smurf. I was doing some experiments like that this weekend. This week, I was. I'm turning this one up, by the way. I put some water on a sound plate and was, sending a bunch of sound waves through water. It looks pretty cool. I might be able to make a video of that someday, if I see an interesting effect. Vermilion is a red. I don't know who that is, Dane. Help me out a little bit. Lawrence. Precipice. We're going fast there, Rantos. I'm almost full speed over here on the right. And we are. We got full speed over here on the right. You can see that vortex getting down there. Let's make it nice and red over here. Make it nice and red over here. What's the coolest thing you've ever done? I don't know, man. That's in the eye of the beholder. For my opinion, I did some experiments where I tested the Coca-Mentos experiment at different elevations. So we went all the way to the top of Pikes Peak, and we went down below sea level in Death Valley, and we looked at a bunch of elevations in between, and we looked at how well the reaction worked at different elevations. It was a lot of fun. All right, here we go. Let's add some bass. See if we can get the double rainbow going. Somebody asked for that. 1, 2, 3. 1, 2, 3, 4. Let's see if we can get it. Let's see if we can get it. I'm not sure we got it. Yeah, I think I missed it. Professor of handstands. Well, I probably believe you're probably good at them, huh? Can you turn the left one? Goofy, this is what happens over here. I'm going to go ahead and do it. Watch what happens. We're going full speed over here on the left. It gets knocked out of orbit. So that's kind of boring. That's usually what happens. I'm going to leave it off, though, and we're going to mess around here. So I'm going to add a bunch of acid over here. And then we're going to chase that with a bit of base, and we're going to see what happens, okay? Let's see what we get over there on the left. Bill Nye or Mark Rober as best children's science educator. Let me know what you think in the chat. Bill Nye versus Mark Rober. Who's better? Push Praj, how to become a professor in the States. You're going to need to at least get a master's degree in your, your respective discipline. It's better to get a PhD, and it's better yet to do a postdoc. Slow is cool, isn't it? Most people are saying Mark, it looks like. Thank you there, Goofy. Let's add a bit of acid over here. We'll slow this one down, too, just for the heck of it. Yeah, it's looking like it's pretty unanimous Mark Rober, huh? Yes, I am, Dino. All right, I'm going to turn this one off. Can I mix purple and orange, Fatima? Yeah, we might do that. Here we go. Let's do this a little bit here. Lawrence Principi is a true professor of the humanities at Johns Hopkins Department of History and Science. Cool, man. I'll check him out, Dane. Thank you. Lawrence M. Principi, I think is the name. What's a Pythagorean theorem? Come on, man. It does look mystical. Could I mix yellow and magenta? Yeah, maybe in a second. We're going to let this play out here for a bit. I don't know, handstand, man. That's beauty's in the eye of the beholder. I personally think it's quite beautiful, but, some people like a little more action. I think it's gorgeous. Let's get a close-up, huh? See, it almost looks like a purple cloud in there. And over here we got like a rotating, I don't know. What happened if you drank sodium hydroxide? It would burn your throat. Ah, Bali, I'd love to help you. Push Praj asks, is hydrogen metal or non-metal? Depends on the conditions. Here on Earth, it's almost always a non-metal. However, in the core of Jupiter or in the core of Saturn, hydrogen is actually a metal. Isn't that something? If you turn the left one on and off quickly, it might look cool. All right, Goofy, you got it. It's finally nice to be able to tell you thank you. Oh, thank you there, Nana. I appreciate that. You forgot the squares, Dyson. Thank you there, Dane. Thank you for the subscription. I appreciate that. It would look cool if you add light at the bottom. Hey, let's try that, Mark. Let's try it. Rantos, diffusion takes a lot longer than people tend to think. So there was somebody wanted me to turn this on and off real quick, so I'm going to do that. Here we go. On. Oh, I did it too quick. Let's try again. On, off. All right, we're going to try it again. Hey, great. You know what? EKZ, that's exactly why I'm doing this. It helps me too. Yep. Hey, give me, you know what? I'm somebody that definitely deals with anxiety. I definitely am. Give me a thumbs up if you feel my pain sometimes. For me, it's like worse at night, man. I wake up in the middle of the night and everything seems like a crisis. It's the weirdest thing. And then I get up, it's hard to get back to sleep. And if I finally do, and I wake up in the morning, I'm like, why the heck was I so worried about all that stupid stuff that kept me awake last night? Give me a thumbs up if you know what I'm talking about. All right, here we go. We're going to add a little acid to this. Here we go. I guess I'm the only one that deals with it. A little acid here, a little acid here. See what happens. Yep. All right, Dino. All right, AAR. Yep. Is that right, handstand? What should I be eating? Anxiety can be helped through diet. I'm all ears. JH, I feel you. I see you there. I mean, it takes a bunch of these are gorgeous. Man, these are pretty. Opinion on transmutation. Dane, I don't think the ancients were very good at that, but, we can do it today in nuclear reactions. Got it. It's like Aaron. Aaron Santora. Got it. Gigabean, I see you. Green foods have a calming effect on the mind. You would not believe how much cilantro I eat, handstand man. It makes me wonder if I like it so much because I somewhere recognize it's good for me. These are gorgeous. Brian, help me out. Adaptogens. Nice there, abstractor. Emerging fields in chemistry. Nico, I've already done that, so I want you to go to my YouTube shorts, and I want you to, I've done 2 videos on piranha acid. I put a scrub daddy in it. You can tell me what you think. What is this? It is some universal indicator added to water, and then I just add acid or base, and watch the beauty unfold. Let's get a close-up there. Look at that. Oh, yeah, somebody said I should put the light underneath it. I didn't do that, so let me try that and just see what happens. Yeah, that is Kenny. Sorry, Fenny. You're going to want to look up the traffic light reaction or the blue bottle reaction. Is there more matter after plasma? Well, I would say there's more matter like below solid. So, there's this thing called the Bose-Einstein condensate. I can't tell what that looks like, but that was the suggestion, to put it below. It's hard for me to see. Yeah, it looks pretty. Yeah, I like that. I wish I could balance it. Yeah, I like it. It looks real nice. Yeah, I like that a lot. I got to figure out how to do that. Good call. Real nice call. I like that. It was a real nice touch. So thank you for that suggestion. Thank you there, Brian. So no, Dino, that's not a dumb question. I wouldn't drink this because it would end the live in about 10 minutes, and that's not because I die, but because one of the dyes in here is a laxative. I don't have any of that push Praj, but if you'd like to see that, I have some videos where I do put sodium in water. Nice. Thank you, handstand man. What a great question. Do you know that, Push Praj? I do not. Or is it Push Pry? The question is, who discovered water as H2O? I'm going to guess it was Priestley, but I don't know. Look at that, man. I don't have any with me, Dyson. So I was right when I said Priestley. Priestley discovered water as H2O. That would have been my guess. All right, I'm getting to the point here where I'm going to probably stop the live soon. And what I do at the end is I strobe light Papa Smurf. Come on, man. I don't know if any. So at the end of the live, I just I turn the camera around, and you can see my ugly mug if you wish. So I'm just warning you, that's coming, and it's time to get out of here if you don't want to see that. It does look beautiful. If I slide the glass to the magnet, it's closer to the wall of the glass. It might curve the whirlpool. Goofy, I apologize. I don't understand. What are my views on G block elements? I'm not aware of any, Push Pry. How about you? I'm not aware of any. Ain't happening, Nico. Hello, Randall. I know, handstand. Come on, Push Pry. You didn't discover a G block element. That'd be a completely new area of the periodic table. It means you've discovered a new element. I'm not buying it. I am not buying it. Hello there, Christy. Okay, 9. So how it turned green. So here's how it turned green. So in each flask, there's some universal indicator, okay? And universal indicator changes color depending upon pH. Hello there, Anush. And it just must be the case that when mixed, the pH in this flask is going to be like 6 or 7. If you turn it off and you add either acid or base, wrong way. If you turn it off and add either acid or base, then you can get certain regions to be at different pH values, and so they'll display different colors. So right now I'm adding base, and that's why the blue and violets are showing up. And now I'm going to add acid, and acid will impart a red color to this. But the acid and the base neutralize each other. So they're going to, as they neutralize each other, they may form some of these intermediate colors. Thank you there. Very good. I appreciate that very much. Thank you. Thank you there, Fatima. Appreciate it. All right, we're going to turn this around. We're going to let you, sorry there, Grub. We're going to turn this around and we're going to say hello. If you drop fast insulin as low as possible, a lot of fiber. Ah, man, they're coming through pretty quick here. Let's flip this around. All right. Let's see if I can read some of this here. Okay, let's see. Someone's liking benzene. Where can I buy the ingredients of these? You can just get them online. Yeah, here. So this is what I look like. Here, I have to wear these because I can't read, like, you know, I can't read without them. So I got my reading glasses on. Hello, Rantos. What's my favorite reaction intermediate? Push Pry, I think it's Push Pry, likes benzene. My favorite reaction intermediate. You know, off the top of my head, it'd probably be the cobalt citrate intermediate. I'm not blind. I need reading glasses. Orthodiethanyl benzene dianion. I want to check that out, Bilotti. Hey, thanks there. Who said that? Thanks there, Dino. Thanks there, Oof. Hello, Burns. What's my favorite science experiment? Whichever one I'm doing at the time, D. Elliott. Which is most often Coke and Mentos. Not going to do that, Jeffrey. Not going to be doing that. Hello, Gojo. No, not happening. Thank there, handstand man. Is methanol the burned version of methane? Gigabean, you can think of it that way. It's a more oxidized version, but it's got a long way to go. It'll get oxidized all the way to carbon dioxide. So Sniper, if all elements are made of electrons, protons, neutrons, and stars making their energy from something like making helium from hydrogen, how neutron stars make this energy? I apologize, Sniper. I don't understand the question. So my understanding is a neutron star happens when gravity in a star is so strong that, you know, there's a lot of hydrogen in stars, okay? Ton of hydrogen. And which is basically a bunch of protons. And the gravity gets so strong that the electrons in the hydrogen atoms get pushed into the protons and make neutrons. So, you know, the atom, right? You got the center nucleus, and then about, you know, 100 times the distance out is the electron. And that takes up a lot of space. And in these neutron stars, the gravity gets so stinking big that the electron gets pushed into the nucleus, and that converts the proton into a neutron. And so you're taking all that space in the atom, and you're concentrating it into the nucleus. And so the neutron star is made up of neutrons. And that's why they're so stinking dense. Correct me if I'm wrong, y'all. I mean, I'm guessing this, saying this off the top of my head. It's hard to remember all this stuff, but I think that's right. So long, Fatima. Bilotti, you and me both, man. I'm loving some cosmology. Why does Mentos react with Coca-Cola? Asks Dino. So it works like this, Dino. Here's the way it works. In a soda, a carbonated beverage, those things are sealed under a lot of carbon dioxide gas. That's why the bottle feels so stiff. And that carbon dioxide gas, it's in the headspace there. That makes a lot of carbon dioxide get dissolved into the water. So there's a ton of CO2 in the water. And CO2 does not dissolve well in water at all. I mean, if you just drink a glass of water, out here in the air, it doesn't taste fizzy. So that's why they have to seal it under CO2 to get the CO2 to go into the water. Well, as soon as you open that soda pop bottle, this carbon dioxide starts to escape. And it starts to escape, and that CO2 is going to continue to escape until it's just like regular old water. And that fortunately, it takes a long time, because if it all happened at once, you know, you'd open a soda bottle and it would make a mess. But it also, because it happens slowly, that allows a lot of carbon dioxide to remain in the carbonated beverage, and you know, that allows us to experience the pop of the carbonated beverage, because there's still a bunch of CO2 in there. But if you think about it, you know, when you first open a soda pop, there's a bunch of CO2 dissolved that, so to speak, wants to come out. Well, here's the issue. Here's why it happens so slowly. In order for the carbon dioxide to escape a soda, a carbonated beverage, it has to make a bubble. But think about this. In order to make a bubble in a fluid, you've got to push away all the water molecules, right? The gas has to push away the water molecules. And that takes an enormous amount of energy. And that's why it happens so doggone slowly, is because there's this huge energy barrier for the dissolved carbon dioxide. Just like sugar dissolves in water, carbon dioxide dissolves in water, and that dissolved carbon dioxide has to make bubbles. And again, there's a huge energy barrier for this happening, which is why it happens slowly. But if you could figure out a way to put a bunch of already made bubbles, pre-made bubbles, and you can stick those inside the soda pop, if you can do that, then you've removed this energy barrier. There's already bubbles inside the soda pop. And then all the dissolved CO2 has to do is get inside the ready-made bubbles, and out goes the mixture. So that's what happens when you add a Mentos to a soda pop. The Mentos go in, and there's little nooks and crannies in the Mentos that aren't wetted. In other words, the water can't weasel its way all the way down into those nooks and crannies. And because of that, when you add the Mentos, there's a bunch of air bubbles in those little nooks and crannies. We call them nucleation sites. And since all of those little nooks and crannies all have a bunch of little bubbles, it creates an enormous number of escape routes for the dissolved carbon dioxide to form the bubbles, and that's why it happens so rapidly. So sorry, that's a really long explanation, but you know, I've written a bunch of articles on the Coke and Mentos experiments, and I guess you asked the wrong guy. I'm in my 50s, JH. Hey, thanks, Hope Rock. JH, I'm in my 50s. Enough spam, all right? Hey, thanks for the question, Snipe. How does gelatin become jelly? I have forgotten, Oof. I'm not going to answer that. Yes, I do teach students, Cooley. Thank you there, Rantos. What happens if you touch a very dangerous acid? It's not going to end well for you. It's going to burn you. Yes, Nico, carbon dioxide indeed gives soda its acidic properties, but you should also recognize that to colas, like Coca-Cola, Pepsi-Cola, they add phosphoric acid, and to like the Sprites, they add citric acid. So there are also acidic properties in sodas that come from the additions. And hey, there's another YouTube short that I did on where I tested. It's not, you know, a precise test, but nevertheless, I did a test to see which has more acid in it, Diet, or I should say Sprite Zero, or regular Sprite. So you check out my most recent YouTube shorts. You'll see a YouTube short where I did that test. Gojo, what happens if you touch a very weak acid? Gojo, you do that all the time. So anytime you drink orange juice, or anytime you use like vinegar, like oil and vinegar, vinegar's got acetic acid in it, which is a weak acid, and you know, citrus fruits have citric acid in it, which is a weak acid. And there's a bunch of weak acids running through your body, and indeed there's a strong acid in your body. Hydrochloric acid's in your stomach. So what's this question here? So leaving a soda out means that only by reaching the surface CO2 can leave. How's that possible if CO2 is more dense? So Coolio, think about this. The CO2 is dissolved in the soda, correct? And just like if I take a sip of the very top of the soda, it tastes sweet, even though sugar is more dense than water. See, when something becomes dissolved in water, it becomes completely mixed all the way through. So because when we dissolve sugar in water, we can taste it at the top and at the bottom, the same is true of carbon dioxide. When carbon dioxide is dissolved in water, it's going to be completely dispersed evenly throughout the fluid. And so there you have it, the carbon dioxide at the surface. In a sense, the carbon dioxide at the surface sees the entire atmosphere as this huge bubble into which it can easily escape. What happens when you touch plasmas? That's not, and then end well. Does the acid in sodas, are they bad for you? No, Rantos, not at all. Yeah, isn't that crazy, Burns? Yeah, the pH carbonated water tends to be, if you carbonate water, the pH drops dramatically. Sounds like fun, Papa Smurf. What happens when you touch plasma? It doesn't end well. Thanks, Coolio, for the question. Indeed, liquid CO2, if it's pure liquid CO2, it's just CO2, it's going to be very cold. But CO2 dissolved in water, that's not liquid CO2. Just like liquid sugar, we can imagine what liquid sugar is. You'd have to melt the sugar. Liquid sugar is different than sugar dissolved in water. What's the strongest acid to exist? JH, to my knowledge, it's fluorantimonic acids. What does sodium hydroxide produce when it reacts with aluminum? It produces hydrogen gas. That's right, M1V1. You can dissolve gas and water. And if you think about this, this makes sense. See, fish need oxygen to breathe. And they don't get the oxygen from the H2O in water. They get their oxygen the same form that we need it, O2, the oxygen molecule. We can get it from the air. The fish get it from dissolved O2 in water. All right, folks. I think I heard my wife is home. I usually do these lives when she's gone to do some yoga, and I would like to see my wife. So I thank you for hanging out with me and checking out some of the beauty of science. Man, did we see some beautiful reactions tonight. And, seeing the beauty of science is really kind of easy. You just got to pay attention to the world around you. I mean, it's like the whole stinking thing is magic. I mean, just looking at a cloud can be magical if you pay attention. Hearing the rustling of a brook can be magical if you pay attention. So just do that sometimes. Try to look at the world with fresh eyes. Be a stranger to the ordinary, and the beauty that will arise to your eyes, become evident to your eyes is remarkable. So thanks for hanging out here with me tonight, folks. Holidays are coming here in the United States, so I'm not sure I'm going to do much more this weekend, but maybe we'll catch you next week, okay? So long, folks. Thanks, EKZ. Love from the B block. I'm loving it. You guys are awesome, and we'll see you next